Okay, so we left off here with these Lewis structures. Again, it's an online test where you won't be drawing these, but for those that have to take bio majors, take OChem, uh, I'm pretty sure no matter where you take the organic chemistry, you'll have to actually draw the molecules yourself. So this problem before started at 59, walked us through, right, with all these little steps, right? You want to connect them all. Hydrogens only make one bond, so they're always going to be terminal or, like the leaf at the end of a branch. And that's kind of, this is a branching type system. You want the highest connectivity and the least electronegative, which if you have this up, this is worth taping up on your wall. And as you start to do this stuff, you just know it. But the element with forming the most bonds is almost always going to be the central atom. Right, so you need all the valence electrons. Remember, those are just the S and P. Then start drawing single bonds, connecting them all, then use the rest of the electrons to put them in as lone pairs, and then approach your octet rule, right? And so the difference between the last two was that lone pair that was here on this oxygen got pushed in to make the double bond. And you can't go over 8 electrons, right? So I know that the nitrogen, we'll see the values coming up for this, +1 and -1. We haven't gotten there yet, but the nitrogen typically has 3 bonds and a lone pair, while the oxygen usually has 2 lone pairs and 2 bonds like the other 2 oxygens. But this is a better structure here on 61 than it is on 60 here, right? This nitrogen doesn't have 8 electrons around. All right, let me go full screen here. Move a couple things. All right, so then the animation here too is good for you to go back and practice at. Pull out a sheet of paper and see if you can do it. And if you get stuck, you hit the next animation and move on. Okay, so the CO2 carbon has 4, oxygen has 8. Sorry, 6. I was reading anyway. 6 and 6 is 12 plus 4 is 16. We want 8 around every element. You would draw a single bond between the 2 carbons from the carbon to the oxygen on either side, right? Then we'd put in lone pairs just like we did before. So there'd be 6 pairs of lone pairs around each oxygen. And the oxygens would be fine, but the problem is that the carbon is missing electrons. So if we put, just like we did in the last one, we push 2 electrons in on each side and we make carbon oxygen double bonds. And now CO2 is a really happy molecule. We saw this in the last one where you have these deviations away from ideal. And with CO2, the carbon is forming 4 bonds, which is what it wants, and both oxygens, 2 lone pairs and 2 bonds. And you basically see the same motif. I'm not going to go through and do them all. That would kind of take a while, but notice phosphorus is below nitrogen, right? Oxygen is rarely the central atom. So in this one, phosphorus is in the middle, right? Sulfur is less electronegative below oxygen. It has the expanded octet, which we haven't gotten into too deep here, but we will, right? And this one would be, hydrogen is terminal or capping only 1 bond. So the phosphorus certainly must be connecting it, otherwise the molecule ends. Here's another one of these NO similar to the nitric acid above, right? One oxygen looks normal and the other one does not, but it's the only way to do this. And so things that don't take that standard motif are going to be more reactive than things that have the perfect motif. Like up above here, CO2 is a very non-reactive molecule. It's what's used in fire extinguishers and, comes out the tailpipe of your car, et cetera, et cetera. Okay, so what was missing from there is formal charge. And so what formal charge is During the bonding, right, atoms may wind up with more or less electrons in order to fill octets. This results in having atoms having a formal charge. So it's a difference in the number of electrons than the standard that we saw. Oops. Let me go back. On what slide is it? On slide 57 here. These are these typical happiest bonding motifs, but we can go beyond these, and there's a charge way of doing it. So when you have more or less electrons than the element brought on its own, then that's what's called a formal charge. Right, so what is the formal charge? You take those valence electrons. So for example, this one's doing SO3 or SO2. Sulfur and oxygen are same place in the periodic table, the same group or column, right? So 6, and then it does, you go through element by element. So 2 lone pairs, that's the 4. And then half of the bonding electrons. And everything we saw on slide 57 had a formal charge of 0. It was the normal bonding. So in this one, right, the oxygen on the left looks normal, right? It didn't draw the bonds in here, but 2 electrons per bond, so that's an oxygen double bond with 2 lone pairs. That's normal. The sulfur's right below and is pretty much the same as oxygen. And so here we have the sulfur has a double bond and then a single bond. So 6 bonding electrons and only the 1 lone pair. And so this gets a +1 associated with it. And then the other oxygen has a -1. So these formal charges, you want to try to minimize these as much in these different Lewis bond, Lewis structures. And the overall charge that you see on the molecule is the sum of these formal charges. So the lower the formal charge, the more stable the molecule. And it has to equal that ion charge number that we've already seen and known. Okay, so here's just the one we just did, right? SO2. Now let's take a look at this molecule. This is acetic acid or vinegar. Right, the hydrogens all are forming 1 bond. This carbon here, 4 bonds, that's all normal. This carbon, 2 singles and a double, so that's what it normally does. This oxygen here, 2 singles, 2 lone pairs, so that's normal. Then the oxygen here, 2 double bonds and 2 lone pairs. So everything is 0 formal charge-wise, and then the overall is 0 for the one on the right. So what this really gets us to is the normal bonding up top, the +1 formal charge we see here, which with the exception of carbon, all it is for nitrogen, oxygen, and then, group 7, fluorine in this instance, is you've added 1 more bond and it's positively charged, which is sort of a good way to memorize it. So this right here you see with 3 bonds and a plus, you don't see this too often. And you won't see it in our class till you get to OChem. So again, 66 is really slide 66 is the full version. Then down below, it's where you're missing 1 bond from the normal motif and you have a minus sign, right? So this is what that example looked like, where we took the lone pair and pushed it in and made it normal. All right, so if we come back to those same ones we've already done, sorry, the animation's a little screwy. We already did CO2, they were all normal, so 0. And these will start to jump out at you, right? So this strange, selenium OF thing, the fluorines are normal, 1 bond, 3 lone pairs. The selenium is right below oxygen, so it should look the same. And we've got that similar situation where the selenium has 3 bonds and 1 lone pair, so that's a +1. The oxygen has the opposite, 3 lone pairs and 1 bond, so that's a -1. So those two cancel and it's still neutral. Here's the NO2. Right, the oxygen on the left looks normal, the one on the right does not. It's got the 3 lone pairs and 1 bond, so that's a -1. The nitrogen's happy, and so the overall charge is -1. Up here, the phosphoric acid, the HOs all look fine. So it's just this oxygen and the phosphorus that are different from the normal bonding mode. Again, 3 lone pairs, 1 oxygen. You notice we see that a lot. Then the phosphorus is right below nitrogen. So normal would be 3 bonds and a lone pair, but this one has 4 bonds. So the phosphorus is a +1, this oxygen's a -1, but the whole thing's neutral. This is sulfite, polyatomic ion. All 3 oxygens are in the -1 formal charge, 1 bond, 3 lone pairs. But the sulfur, which should normally be like just like oxygen, 2 lone pairs, 2 bonds, has 3 bonds and 1 lone pair. So our sulfur gives us a +1, each of the oxygens a -1, and overall a -2. The P2H4, normal bonding mode, right? Phosphorus is right below nitrogen, so 3 bonds, 1 lone pair. And hydrogen only forms 1 bond, so hydrogen's always the easiest. Okay, so resonance, if you've played an instrument and it's, more specifically something with strings on it, the resonance is sometimes talked about and explained in better detail, but it's the sound you hear is the vibration of the string going back and forth. So why is it brought in here is that, remember, these electrons are moving. We draw them in here, solid lines for bonds and lone pairs, but they're really in those S and P orbitals, and they're moving at, like the speed of light or whatever. So when you have these identical atoms, hold on, there's a cop car going by. Good time to grab a water. So when you have these identical atoms, like the oxygens, in these various examples we've seen, the formal charge can go back and forth. So for example, in this SO2 that we already did, right, the sulfur stays a +1 because it's the same, but you can flip-flop where the -1 versus the normal bonding mode is. And and really what's going on is it bounces back and forth between these two. So when can resonance occur? Well, you have to have at least a double bond and you have to have lone pairs, because otherwise you wouldn't be able to draw it. So if we look at, say, this one over here, the way you would get to the one on the right is if you took 2 of these electrons out of the double bond and put them down here as the lone pair. Conversely, to make the normal bonding mode, you would take, as they've drawn it, these 2 electrons here on the oxygen on the right and push them in and make the double bond you see. So you won't have these resonance for hydrogen or fluorine, things that only make 1 bond. It's got to be something that makes conform double bonds and then needs lone pairs. Okay, and I think, you've heard this for cars before. This book's a little out of date, maybe, originally written in 2008, but you've seen and heard of hybrid cars, right? They have electric and gasoline capabilities, and the same thing, here they're showing us a couple dogs, right, where the offspring look halfway in between the two. And so for us in here, and then for people in OChem, this is the kind of thing you see quite a bit, where they show the resonance like this, right? So this is ozone, O3, just like the SO2, right? The oxygen in the middle is never going to be completely happy in that normal mode, it's always going to be a +1, but the oxygen, on the image on the right, it's the oxygen. On the image on the left, the oxygen on the right is the +1, right? And then flip-flopped to the image on the right. So a lot of times this is shown with just a dashed line, and you can basically think about it like a half a bond, right? That the molecule is really oscillating, resonating back and forth. Right, so just a little reminder, but we've talked about and seen ozone, where it comes from. Now looking at the structure of it, and so what it is the light comes in and absorbs and breaks that bond and spits out an oxygen atom. Ben just asked a question. So besides acknowledging why does resonance matter, it's going to affect the behavior, the reactivity of molecules, especially in organic chemistry. And we'll see a few examples coming up. It'll really be important at the end of next chapter. So chapters 9 and 10 here in this book, they're really one big chapter. It's bonding. And near the end of 10, we see a lot of electronic properties that that molecules have, like dyes and graphite, etc. And that's based on resonance and electron movement and whatnot. Good question, though. Okay, so with these structures, the atoms still have to be connected. You can't change, if you disconnect or change the framework, the single bond framework, then it's a different molecule. So the framework has to stay the same. So then the only thing that's moving is the electrons. You got to have the same number of electrons, right? If you take an electron away or add one, it changes. Remember when we did ions, right? It was the chloride ion, or we didn't go through all the naming, but if it was iron, it would be iron metal versus iron 2, the ion. So the number of electrons has to stay the same. So second row elements, that's that octet. That's second row, remember, is carbon, nitrogen, oxygen, fluorine. And this is due to those orbitals that we looked at in the previous chapter, right? Second row has only access to S and P, total of 8. It never does this expanded thing that the third row can do. The reason the third row can do it is because those d orbitals now, as you move further away, right, the orbitals get closer and closer together by the 1 over n squared, and the d orbitals, the 3d ones, are close enough in energy to use to do bonding. We won't do much expanded octet, maybe 1 or 2 problems or something. Formal charges must be the same. So if you have the same number of electrons, then the formal charge can't change. Right, then here's where the subtlety comes in. Better structures have less formal charges. Then better structures have smaller formal charges. And then this is rare that you'll come to a problem, a molecule, you'll have this distinction, but it's also true. This is pretty rare. You'd have to have a bigger and complex molecule. And you'll see this more in organic chemistry, but it is part of the rules, is that if you do have the formal charge, you want to have it on more electronegative atoms. And we saw that already when we talked about the covalent bonding, right? That the bond was polar. So if there's an element that's more electronegative, a negative formal charge is going to want to be on there. All right, sorry, quick break. My dog wants out of my room. Okay. All right, so let's now tackle one of these. Here's, I think we did nitric acid, which would just have a hydrogen on here, but this is nitrate, NO3. So our oxygen looks normal for this one, but the other two have only one bond and 3 electrons, so that's a -1. The nitrogen doesn't have that lone pair and has 4 bonds instead of 3, so that's a +1. So you can get to the other structures by pushing in a lone pair, making the double bond, and pushing out 2 of the electrons from the double bond and into a lone pair. And so you can alternate which oxygen has the minus charge on it. But the nitrogen maintains it. All right, again, we always follow the octet rule. Less you're in the third row, then if you need to, you can put more electrons around these third row elements, and that's due to those d orbitals being close energetically. The other exception is odd numbered of electron species, which we'll cover in greater detail, and it'll make more sense when we finish up the next chapter. These things are really reactive. And you might see these if you're super into health and like fitness and diet things, where they'll say, you know, taking different supplements to stop free radical damage in your body. It is true. So vitamin C is one of the classic things. You hear the term antioxidant. And so the free radical, these things that have one electron, they want to give up the electron. And that causes chemistry reactions, things to happen. And it doesn't do it softly and intentionally. It does it it gets rid of the electron indiscriminately, and it'll react with anything around it, which is not usually the way you want things done. And then up high in the periodic table are these stranger elements, right? Carbon's normal, then when you move over one boron, doesn't necessarily need 8 electrons. Sometimes it's happy with 6. And aluminum right below it is, you know, in some of the periodic tables, it's labeled as a metal. So again, you might see an example or two in here, but those are really more for organic chemistry because they do unique reactions, and we'll just mention them in here. All right, so to draw these, you got to do the Lewis structures we covered last time. I'm still working through them. Started putting in those formal charges. Notice where the electron pairs, you can move them, the minus and plus charge. Is it a second row? Only move the electrons if you can move them out from those multiple bonds. In the third row on, you can put in more electrons and do the expanded octet if needed. All right, so let's take a look at something that you may have already used in lab, and you certainly will, especially bio people. This is H2SO4, which is sulfuric acid. So here's just the basic framework put together, right? No multiple bonds yet. So we've got the hydrogens are fine. We can ignore those. It's only one bond. The oxygens on the far left and right with the hydrogen attached to them, that's the normal bonding mode, so they're fine. So really, it's just our oxygen and the sulfur. So as is typical, right, this is the lone pairs could be pushed in and make a multiple bond. The oxygen is the -1 for both of them. They both look like that. The sulfur is just like oxygen, where it really wants to do 2 electrons, 2 lone pairs and just 2 bonds. This one's beyond that. It's got 4 bonds. So a +2. Right? If we push in and do those normal bonding mode for oxygen, we make a double bond. And so those 2 oxygens go to 0 instead of the -1 formal charge. And then what would the charge be on the sulfur? Well, it can do the expanded octet. And it's got plenty of room because those d orbitals, there's 5 orbitals there. So the normal formal charge for these expanded octet problems doesn't work because we don't need to assign a number to it because it's a third row and it's got 5 d orbitals. So if we come back and look at those the same ones we looked at, right, our minus 1 plus 1, minus 1, everything looks pretty similar. And we can start the ones that had the charge and say, for this SeOF2, right, it's really just going back and forth. And which one of these is better? It's obviously the one with no charge on it, right? So the one on the right. For the NO2, the nitrite, they're identical, right? It's symmetric. The phosphorus, this is phosphoric acid. Notice that it looks a lot like the sulfuric acid, right? So when we push it in, then the phosphorus is third row, the expanded octet, so there's no formal charge because there's plenty of electrons. That takes the oxygen and everything else to 0, so the one on the right is obviously much better. For SO3, all the sulfurs are the same. So the one in the middle, right, is sulfurs are +1 and the oxygens are all -1. So what's better is to push one of them in. And then the oxygens are all the same, so you can rotate around which oxygen has the double bond. And the H4P2 one, like CO2, was already happy. There was no charge and no issues. Okay, so sort of a shift in gears. But this is all building. Again, chapters 9 and 10 are really just one big giant chapter. So now we covered the heat of a reaction, and then we moved on and we talked about the orbitals and the bonding. And what we're doing here is we're going to revisit the bonding energy. And now that we know about the bonds, there's a more detailed way of keeping track of the energy in a reaction. So all these chemical reactions involve breaking bonds and making new ones, right? The chemical formulas changed. Our most common example was like methane, CH4 going to CO2 and water. And so now we're going to have this table where we have the bond energies, and we can tabulate up and keep track and count up the energy expected by the actual individual bonds. Again, we saw these for the ionization energy and stuff like that. Everything's studied in the gas phase. It doesn't really matter. We're just going to use the values. And homolytically means versus heterolytically means that you're breaking the bond apart. Heterolytically means uneven. So the 2 electrons go with one atom from the bond and the other doesn't get any. Homolytically would be when 1 electron from each, from the bond goes with each atom. All right, the more electrons 2 atoms share, the stronger the bond, which makes sense in the picture that we saw when we started learning about this, that it's the nucleus with the positive charge, and the electrons are negatively charged and put in between the two. And so the negative charge in between held the 2 bonds, the 2 nucleus together. So the more electrons you have, the stronger the bond's going to be. It's quite a bit more complicated than that, but for now, this is what we'll do, and then we'll explain why it's more complicated next chapter. But you can kind of already see it here, where like CC, for example, is almost 350, but the double bond isn't 700. Then the triple bond, right, should be what is that? Like 1,050. If it was really, 350 times 1 times 2 times 3. Okay, so that's the number of electrons. Then we studied and talked about radius, the length of the bond. So the shorter the bond, the stronger the bond. So the higher up in the periodic table, the stronger the bond. And this is why we burn and use gasoline and things like that, because it's made of carbon-carbon bonds, which is high up in the periodic table, and hydrogen's at the top. So carbon-hydrogen bonds have a lot of energy. All right, so the way engineers, especially chemical engineers, and this is how they formulate gasoline and things like this, or they did a long time ago, they use these average bond energies, and you can estimate and come up with the heat of a reaction. Instead of having to use the bomb calorimeter and study it, you can just do it by the individual bonds. So this symbol here, if it's been a while, this means summation, right? So we're just taking the energy from a table of the bonds that were broken and adding it all up, and then adding to that the sum of all the bonds formed. So let's take a look at some reaction. This is sort of, week 2 or 3 or something of organic chemistry here, where you've got a carbon-based molecule, methane, natural gas, 1 carbon, 4 hydrogens. It's reacting with chlorine gas, ClCl, right? It's higher in energy to break the bonds apart. So here we've got 2 free atoms of chlorine, and the hydrogen's been broken off. So we broke a CH and a ClCl. That costs some value in energy, whatever it is. And then what do we get back afterwards? We get the energy associated with the new bond. So you get the HCl bond and the carbon-chlorine bond. So you add these two together and you get the overall. So whether it's endothermic or exothermic just depends on the difference between the two. All right, so here's our key table that has all these values that we'll use. You don't have to have any of these memorized. I don't have a single one of these memorized. If there's a problem on the test, it'll have a small table with the bonds that you need. You won't have to come and look it up. But if you do any like worksheet, study guide, come back and revisit any of these problems, this is a good place to go and get it. And these values should all be the same, even if you look it up on like Wikipedia or just Google search it or something. And the reaction just chosen here is hydrogen peroxide, which if you take 1 mole of hydrogen gas and 1 mole of oxygen gas, and then you would get a hydrogen-oxygen single bond, an oxygen-oxygen single bond, and an oxygen-hydrogen, another single bond. All right, so let's do that one. Right, we broke the HH and the double bond. You need to make sure you grab the right, bond when it's double versus single. It makes a difference. So the ones we broke were 436 and 498. So that would be the uphill. That was the cost, right? Then the bonds made, that's released. So this one's going to be negative, whatever it is. We made 2 single bonds, HO single bonds, and then 1 oxygen-oxygen single bond. So the reason it's negative, right, is that's going down. Whenever you go uphill, remember the endothermic versus exothermic. So the negative sign for the energy that you're getting back, you add the two together, and there's our overall. And pretty close to what, just decimal points and etc. off what's listed in the back of the book. All right, so we covered these, the orbitals, and that's where the size and the radius came from. Those two radius coming together is what gives us the bond length, right? And they just take the average one. So this is done for, lots and lots of compounds, and they come up with these average values. So we've got, a couple different trends. So from before, there was the more electrons in there, which, a higher negative charge between two positive charges makes sense that it should be higher in energy. And then it's also should be shorter. So we see this trend that the, triple versus double versus single, the bond is shorter, the more multiple bonds, and the energy's higher. And we'll come back to these double and triple bonds next chapter as well. Then there's a little decrease from left to right across the periodic table due to electronegativity. Then down the column is obvious. We already covered that. That's just the orbitals, right? So fluorine would be N equals 2 versus chlorine 3 versus bromine 4, etc. Iodine would be after that. So here's a shorter version of this. What's the difference? Let me go back. The other one seemed like, yeah, there's a lot more stuff in here. Just a lot more bonds. There's sulfur and fluorine and iodine and stuff like that. Whereas this one is more of the classic and typical. This is more of what you would need in OChem. Here's some acids that you would use, and then amino acids, and essentially whatever it is, 99.9% of the human body is made up of carbon, nitrogen, oxygen, hydrogen, and there's a little bit of chlorine and sulfur, and not nitrogen, but chlorine and sulfur and other atoms. Okay, so notice we've covered the bonding right here: ionic and covalent, and now metallic. Ionic, I think there was 10 or 20 slides on it. Then covalent was almost the rest of the chapter. And we'll see here, metallic is pretty short as well. Then the whole next chapter is revisiting the complexity of covalent bonding. Okay, so just revisit a few things with metals, right? They generally have the pretty low ionization energy, which means they wanted to lose electrons pretty easily, which makes sense because they conduct electricity. So if they're conducting electricity, the electrons must be moving. So basically, the idea here of metallic bonding is that the metal atoms are letting go of those valence electrons, and they're basically shared to every atom in the entire piece, which, keep in mind, remember Avogadro's number, 6.022 times 10 to the 23rd. There's, an enormous number of these atoms. The idea here, the organization of the metal cation island in a sea of electrons, is kind of like the idea of a domino. Like you've seen, the Guinness Book of World Records when someone sets up a domino display. They knocked the domino over, and where they tapped it, the falling domino is what your eye sees, right? Behind it, the dominoes have fallen over, and in front of it, they're still standing up. And that's kind of the way you can think about an electron moving through a piece of metal. And what this means is that the electrons aren't discretely with one particular atom, like we saw in the covalent ones with the formal charge and whatnot. And so the bonding that you see results from this type of idea. And, that's what this picture is trying to show you, is that, right, it's a metal. The sodium is what they picked here, but it's like a never-ending array of these atoms all next to each other. And so if it loses one electron, then it's the idea of like a hole. And that's sort of the domino that's falling over, right? When one atom's missing the electron, an electron from another atom jumps over, and then that happens again and again and again, and it goes on indefinitely, right? A mole, pencil lead is probably like 1 mole or something, or half, and that's 6.022 times 10 to the 23rd atoms. It's kind of a number too big to comprehend. So that's kind of it for the metallic. And so here it just does the typical thing in red, what you already knew, and in black, what hopefully you've taken away from our look at the atomic level of these different bonding modes here, but whatever chemical it is. So you already knew metals conducted electricity, right? You don't go and touch power wires or stick your keys in the socket, because they conduct electricity. So, and then now, why is that? It's that the electrons are in these orbitals and they're free to move and jump from atom to atom. Nothing's stopping them, right? They're not concrete covalent compounds. And this is why you wear gloves or a pot holder when you grab a piece of metal out of the oven, or if you're doing electrical work, because concrete molecules in the covalent bonding sense, they don't conduct electricity. As temperature increases, electrical conductivity decreases. This, I don't know that you knew that beforehand, unless you're really into remote control cars or soldering or something, as when you were younger. But heating causes vibrations, right? So as you heat something, it moves from potentially a solid to a liquid to a gas. And as the ions vibrate faster, it makes it harder for the electrons to make their way through the crystal. This is not really that key of a point. It's just a little foreshadowing for someone who's an engineering student. They conduct heat. You already knew that. And we'll see that a lot of things in energy have to do with electrons moving, and we'll come back to more next chapter on what forms the covalent molecules. But the electrons can move because they're tiny little things, and they can move through the entire substance, the entire piece of metal. And electrons are moving near the speed of light. You've seen metal and aluminum things reflect, and this has to do again with the electrons, and we kind of saw this with the photovoltaic effect, and when you shined a light and what frequency that was to have it eject. So that's just a revisiting. You already knew that they're malleable and ductile, so jewelry and wires. And again, this idea that they're just all connected past right next to one another, and if the electrons can jump from one to the other, there's really the attractive force between that cation and the free electrons is pretty malleable and adjustable, right? And different metals are easier to do this than others. We already saw the high melting points and boiling points. Mercury is the one exception, but we won't get back to that. And it all comes down to that atomic level of the way of looking at it. Then these trends up and down the columns and row is not really relevant for us. Okay, we still have enough time. Quite a bit of time to start. And the next chapter is quite long. Opening slowly here. That one. So Timeline wise, our next exam is next Wednesday. And this one's 150 slides, so it takes quite a bit of time. So we'll see how far we get. Just go. There. Okay, so notice even the title here is Chemical Bonding 2. So it's really all one big chapter. There won't be any focus on the ionic or the metallic anymore. We've covered all there is to it there. There's a little bit of expansion in chapters 11, so you might see it in Chem 162, depending on who you take that with, where there's some of the packing arrays and there's a variety of ways, but it's not that, it's trigonometry and geometry and stuff, but there's only, I think, 7 or 8 ways to pack these ions. But the covalent compounds, again, is organic chemistry, where there's only 1 year of it, but you can go on and get higher degrees in it and spend a lifetime and, become a chemist and work for a pharmaceutical company making new drugs. Sorry, just every time I change the share, it moves things around. All right, so the properties of these substances, these covalent things, they come from the structure. And this is modern organic chemistry, gasoline versus vitamin C. Think of any medicine you've ever taken, and you can go Google and look up the compound. In a lot of ways, that drugs like that work is like a lock and a key, and the drug is like a key that fits in the enzyme, and the enzyme is the lock. So the structure includes several different things, right? The skeletal arrangement, then the type of bonds, and we won't see ionic, and notice it's not that ionic's pretty straightforward. Is you need different ions in your body, right? This is like Gatorade's thing. Electrolytes is the term they use, but it's different ions. But mostly what we'll be looking at is these polar and non-polar bonds. And then here we're just going to enter, basically our shape is going to be focused on just the central atom, and most of our molecules are only going to be 2, 3, 4, 5, maybe 6 atoms. But for people that are going to go on and take OChem, like the human myoglobin, I think, has like 15,000 atoms in it. So the molecules can get really big. Right, and these initial ones tell us the shape, so in 3 dimensions. All right, so this is where it's handy to have that molecular modeling kit. I would, again, I mentioned it before, but I would really recommend for anybody that's going to take OChem, it's almost impossible, I think, to pass and do well in OChem without one of these kits. And they're only like between 10 and 20 bucks. It's a pretty good investment. And then they're hard pieces of plastic. You can always sell it to a friend that's going to take OChem and get your money back anyway. All right, so one of the problems with learning this, and why the modeling kit helps, is when you draw these things or you see drawings of them, that's in 2 dimensions, right? And if you had art classes before, or if you were ever into architecture, this is drawing. They usually start you out with just drawing like a block and shading it and making it look, while you draw it on a flat, 2-dimensional piece of paper, making it look 3-dimensional. Right. The different geometries around the central atom have specific names, and they come from the corner, which sounds a little funny, but it'll make sense once we see some pictures. again, the positions of the surrounding atoms, and it's depends on the corner of that geometric structure. All right, so if you have more than one bond, then there's going to be a bond angle. So how do we get there and make these shapes? You do it from Lewis theory. So this is why last chapter is important, and it's really just one big chapter, is that all these shapes and the three-dimensional network that we see comes from the Lewis structures. So the thing here that becomes important that like didn't seem as important maybe when we were drawing it is the valence electrons. They form the bonds. That's obviously important, but the lone pairs, as they're called, or unshared valence electrons on the outside, have also a much more important effect in the three-dimensional shape. And the idea to this is that, remember, electrons are negatively charged, so they electron groups, lone pairs, etc., they repel one another. So there's a theory that gets you to this, and it's called VSEPR, which stands for valence shell. So valence means S and P electrons. Shell means those orbitals. Electron obviously just means electron. Pair, they come in pairs generally, with the exception of the free radical, but that's a very rare exception. And then repulsion, because they're negatively charged, so they repel one another. Right, and this is what gives us these geometry, shapes, and bond angles. So this is kind of the idea where you'll have your central atom here. The two electrons mean there's a bond between these atoms, but these electrons are repelling each other. So when you have one atom and you have three electrons, atoms bonded around it, the electrons push the atoms as far away from one another. And so basically what this usually means is the number of atoms around the central atom divide 360, right, as a circle, you divide that by the number that's there. Right, so our Lewis structure tells us the arrangement. Each lone pair of the electrons tells us is considered a group. Then each bond is also considered a group. And it doesn't matter whether it's a single, double, or triple bond, we still call that one electron group because it's in the same location. So let's do an example. Right, here's our NO2 with the now we don't care so much about the formal charge at the moment, but +1 and -1. But more critically is we have a nitrogen with one lone pair, one double bond, and one single bond. So the lone pair is an electron group. The single bond is an electron group, and then the double bond is an electron group. So even though there's 8 electrons around it, the electrons are only in 3 areas. So there's only a couple different ways to arrange these, because really in organic chemistry, you only have 4 atoms around a central atom, and that's because carbon only forms 4 bonds. There are the expanded octet situations, and we'll do a few of those, but most of this is setting you up for organic chemistry. So there's a couple of basic arrangements, and our maximum here is just a 6. We'll see that, and 5 and 6 atoms around a central atom isn't that common, and it's not that important for organic chemistry. Most of it's based on carbon. So in order for the molecular shape and the bond angles to be perfect, perfect geometry, all the electron groups must be bonds, and all bonds must be equivalent, but we know that they're not. So usually the shapes are a little distorted because some bonds are longer, some atoms are bigger. You can have more lone pairs on one atom, etc. For molecules with resonance, it doesn't matter which resonance you pick because the molecule is the same. And we'll see examples. All right, so the simplest, then, here's an example with beryllium, but it's really silly. Like, I've never used beryllium dichloride is what this is called, but we'll breathe out CO2, so it's a much better example. And it's the product of all, combustion. So obviously, if there's one atom, there's no shape to it. If there's two atoms, it's a single bond, there's no shape. So you don't get any defined shape until you have 3 atoms and 2 electron groups. And it's not much of a shape, right? It's just linear. So the double bonds around the carbon want to be as far away from one another as possible. And that's exactly 180 degrees, right? The other side. And so, this is the first one. That's pretty straightforward. It's the easiest. These are kind of handy. One of the ways that you learn this in modeling is since balloons take up space, it forces it to look correctly. So it's kind of a good demo. So if you take 2 balloons, right, the carbon would be where the balloon's tied in a knot. You put those together, right? The balloons space-wise repel each other, and so it matches what the CO2 looks like on the atomic level. And then I don't know why this is in here, but it's kind of funny. I don't know what this thing at the bottom really is supposed to tell us. Okay, so there's other examples, but they chose this one because in OChem you will see a few things that have 3 atoms attached to boron. It's that exception where it can make a 4th bond or it can be fairly stable with just 3. But the important part here to us is that there's 3 electron groups around it. So it stays within a flat plane. And if you just divide 360 by 3, you get 120. So here's sort of the difference of last chapter. You might draw it like this, but over here is what's really correct, right? Not 180 and 90 degrees, but that they should all be 120, right? All the bonds, the elements are the same. It's boron, 2, 3 fluorines. So there's no difference between them, and it should be nice and symmetric. If it was, say, boron, 1 fluorine, 1 hydrogen, and 1 chlorine, then the electronegativity is different. The lone pairs on, fluorine and chlorine are different. Hydrogen doesn't have it, and you see some bowing and stretching and non-ideal or non-perfect bond angles. The NO3 that we covered is a better sort of example since we already did it, where we had those 2 formal charge of -1 were the same in the resonance, and then the carbon-carbon double bond. This is why single versus double is still 1 electron group, and really the double bond is bouncing over to each of the other bonds, and it's really more like 1 1/3 bond to each oxygen, right? Again, the electrons are moving at near the speed of light, but it's all 3 the same element attached to nitrogen, so the bonds lengths and angles should all be perfect. And 360 divided by 3. Okay, so what about an example like that? Again, on the left is the way you might have drawn it before, but in the future and for OChem, when you do have to draw it, it should be something closer to that. Central atom, double bond is the same as 1 electron group. Doesn't matter whether it's single, double, triple. So we've got 3 groups around a central atom, and now we have hydrogen, the smallest atom, and so the oxygen, its lone pairs, and it's going to push these little atoms further down. And you don't need to memorize these, and you won't be graded on not drawing it to the bond angle. It's just explaining how, especially into the world of organic chemistry, that it doesn't take on perfect angles. There's some flexibility. So the picture on the left is kind of useful. This thing on the right almost looks like a blob of cookie dough or something. I don't know how helpful that is. All right, this is generally the first shape that gives people a little bit of trouble. And again, this is where the modeling kit becomes really helpful at the beginning of it. When you have 4 electron groups or 4 atoms, then you get this tetrahedral geometry. And again, on the left is sort of what it would look like before, but this is really a cross or a T. And that's not really what it takes. It takes on the shape of sort of a tripod, like where you would, have this set up with your camera, say the green sphere on the top, right? The 3 legs are spread out at 120 degrees, but then the black and this one carbon, where your tripod, the stand comes together, isn't on flat on the ground. It's up above it. And so this angle, it isn't 90 degrees, but it's not 120 either. And it turns out it's 109.5. So again, on the left was the way you might have drawn it last chapter. Right in the middle is the way you want to start to think about it from now on. And this should be a number you memorize, 109.5 for tetrahedral. And then, the thing on the right, again, looks like, I don't know, a lump of cookie dough before it goes in the oven. And so if you've studied, ancient history, this is the pyramids where they buried kings, things like that. And the king was always buried in the center of the pyramid. And that's sort of the idea here, where each corner of the pyramid is where an atom would be, and the central atom would be in the middle of the volume. So 4 balloons works as well. And so it's a tetrahedron where the base or all the sides are triangles. And the reason this is so important is because carbon forms 4 bonds. So gasoline and, all the important organic molecules, vitamin C, nicotine, your blood, amino acids, et cetera, almost everything has carbon backbone and framework to it. We are mostly made of carbon, human beings. You have other, there's metals inside you, and there's nitrogen and oxygen, obviously, as well, but carbon is the framework for everything. Okay, so those are the more important ones. There'll be one on the test of these higher ones. So that's where there's 4 bonds, right? Carbon, 4 things attached. You can have, with the expanded octet, you can have things with 5 and 6 atoms attached. And that's what we'll see here. So this shape is called trigonal bipyramidal. So a little bit wordy, but it's because it's has a triangular pattern and then sort of 2 pyramids slapped on top of one another. And kind of like the way the Earth rotates, the equator, right, is the middle, except this isn't, a sphere, it's triangular. Then the top is the poles, and they're called the axis. So what this really looks like is the tetrahedron from last geometry, last slides. If you slap those 2 together, right, there's the triangle. It looks just like before, but instead of just 1 atom at the top, there's a second. And so if you took 5 balloons and tied them together, you would get 3 in the equator, the equatorial, forming, just like several slides ago, 120 degrees, and then perpendicular up, right, 90, there would be an atom on the top and the bottom. And so this only happens in expanded octets. So your central atom has to be something in the third row, which in the world of organic chemistry, you have less and less atoms in the third row. It's mostly focused on second row atoms. Yeah, and again, over here on the right, I don't know how helpful this blobby looking thing really is. All right, so you can see we're obviously going and adding one more atom on here. And this one is a bit easier, actually, I think, because you've got a sixth group. It's called octahedral due to the octahedron shape, but now everything is equivalent. So before you had the 120 degrees and the 90 degrees, but now, just go to the picture. Now it's a square with an atom on the top and the bottom. But everything's 90 degrees, so it doesn't matter which way you turn it, right? So in this shape, this octahedron shape, the face is a triangle, but every side of it looks identical. It doesn't matter which way you twist or turn it. Again, I really recommend for anybody that's got to take OChem and you know it, you may as well go buy the modeling kit now. Again, the expanded octet. There's no other way to do this. Carbon can't do this. You can't have, 5 or 6 electron groups unless you have d orbitals to put electrons in there, and then it looks symmetric. So SF6 is a gas, actually, and gets used in the computer industry, production industry. Again, like how you might have drawn it before, that doesn't really give you much information, and then what we know now. And so the picture on the right is, trying to show you that depth perception. Again, the one on the left is kind of useful, but this thing on the right just looks like, I don't know, cut in half tennis balls stuck together. I don't know that that tells you too much. We've only got a minute or two left, and next we'll go in and look at what the effect of lone pairs does, but it'll affect each shape. So I think that's a good place to stop. So we'll pick up here on Wednesday and look at how instead of a bond there, like for example the last one where it was a central atom and 6 bonds, there'll be a central atom with 5 bonds and 1 lone pair, and see how the lone pair bends the shape. Here. So I hit the unmute. So sort of the standard questions, comments, thoughts, feelings, if you want to chat about anything. If not, then have a good day, and I'll see you on Wednesday.
All right, and you said our test is next week's Wednesday?
I think it's the 19th, which, yeah, so today's the 10th. Wednesday will be the 12th. So we'll review next Monday. Whatever we get to this Wednesday will be the cutoff, and same as previously, where no new material the day before an exam, their lecture before. So whatever we get to on Wednesday, that's it. And then we'll review study guide, worksheet, some combo of those things on Monday, and then test is next Wednesday.
All right, have a good one. See you Wednesday.
Cool.
Thank you, Professor.
Yeah, no problem. Have a good day.
Me too. Bye-bye.
Bye.